All right. So, namaste everyone. So let us begin our discussion for the day. Okay, so let's do a quick recap of what we have done so far. Okay, so in the past four lectures, we have primarily concentrated on reviewing some algebraic preliminaries, right? So if you recall, we understood a notion of a group, then we understood a notion of a field. Okay, then we tried understanding what are vector spaces, and then we tried understanding what are subspaces and subgroups and so on, and then finally we defined this idea of a quotient space, right? So so far, I mean, as a student, I mean, it wouldn't be clear to you why are we doing all these and so on and so forth. Okay, so I understand this this mindset. Okay, so from today onwards, okay, we will shift gears, and we will talk about its applications, that is the applications of these different preliminary objects that we studied to in the context of simplicial homology. Okay, and throughout this course we will focus on simplicial homology over Z2 coefficients. Okay, so by that I mean we'll be working with some vector spaces, and if you recall, a vector space has an underlying field. Okay, so that underlying field for us throughout this course will be these Z2 coefficients. Okay, so that's what I wanted to stress when I say that we'll be studying simplicial homology over Z2 coefficients. All right. So what is Z2? So recall Z2 is a field made up of exactly two elements. Okay, and we represent these elements by 0 and 1. Right. So since it's a field, I have to tell you what the addition and multiplication operations are. Well, the addition operation is very easy. So 0 plus 1 is 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0, right? And similarly, the multiplication operation is accordingly defined. 0 dot 0 is 0, 0 dot 1 is 1, 0, 1 dot 0 is 0, and 1 dot 1 is 1. Right, so in this way you can see that I have defined the addition and multiplication operations, right? And with this addition and multiplication operations, one can see that this is actually a field, right? So this will be the field of interest for us throughout this course. All right. Okay, so we begin now our study of simplicial homology. So what does that mean? Okay, so let me give a rough motivation. Okay, and then we will sort of do the formal construction that helps us understand what I'm trying to say. So let's say we have these three different simplicial complexes. Okay, so this is example, let's say 1, then we have the second example, and then we have this third example, right? So let's just try and distinguish these through examples, and for simplicity, let's say I label these vertices as v1 v2 v3, I label this again as v1 v2 v3, and I label this as v1 v2 v3. Is that okay? So now our goal is to so in simplicial homology we have abstract simplicial complexes, and our goal is to study its topology. By that I mean we are interested in studying how many holes are there of different dimensions. Okay, so in this particular example, let's say we are interested in studying holes, number of holes of a dimension 3. So dimension 2, sorry, dimension 2. Right. So let's look at the first simplicial complex. So here you can see that there are no enclosed regions of dimension 2. Whereas if you look at the second example, you can see that here is an enclosed region, right? Enclosed region meaning it is covered by these one simplices, that is these edges, one faces, right? And this region is hollow, right? So this is the enclosed region, and this is the two-dimensional hole that we are interested in counting, right? And let's look at this third example, right? So here you have three vertices, here you have also these three edges, and finally we also have this two-dimensional face, which is the triangle, right? So indeed you have some region which looks like perhaps enclosing a hollow region, right? But you can see that because this triangle is present, this hollow region is filled, right? So what I want to say is that in this first example, the number of holes of dimension 2 is 0. In the second example, the number of holes of dimension 2 is 1, right? And in the third example, the number of holes of dimension 2 is again 0, right? So the reason why it is 0 here and the reason why it is 0 here are different. Okay, here there are no enclosed regions, right? Whereas here there are enclosed regions. However, the enclosed region is filled, right? So a hole loosely is a hollow enclosed region. Okay, so you can think of hole, a hole as loosely a hollow enclosed region. Okay, so in this topic of simplicial homology, we will basically build some tools that will enable us to be able to find these numbers. That is, in this simplicial complex, the number of two-dimensional holes is 0. In this simplicial complex, the number of two-dimensional holes is 1, whereas in the final example, it is 0. So this is our goal. Okay, so I hope the goal is clear. I haven't defined to you what a hole is formally. At this point, we will stick with this intuitive definition, and later on we will provide a formal definition of what a hole actually means. Okay, so let me pause here for a second or two. If there are any questions, quick questions with regards to this intuitive motivating example, please let me know. Okay. All right. So I don't see any raised hands, so maybe we can advance. Okay, so now we will be setting up few things. Again, it will be dry and it wouldn't be clear a priori why we are doing this and so on and so forth. So I request everyone to be a little patient, right? Hopefully, at the end of today's class, you will be able to see that what we are constructing will enable us to, find such numbers. Is that okay? All right. So let's do the formal construction. Okay, so what is the setup? Where we have been given some abstract simplicial complex, and let us refer to it as delta. Is that okay? And let's fix a number between 0 and dimension of delta. So recall, the dimension of delta is the dimension of the largest face. Is this okay? Sorry, the largest dimension of the face in the simplicial complex. Is that okay? So what is our goal? So our first goal is to construct a vector space, which we will refer to it as Cp of delta, corresponding to the p faces in delta, right? So let's recall what is a p face. A p face, recall, is a p-dimensional face, okay, which means that this p-dimensional face has p plus 1 vertices. Is that okay? So whenever I say a p face, I equivalently mean a p-dimensional face. And what is that? Well, that is a face in delta with p plus 1 vertices, right? And we want to use these p faces, and we want to construct a vector space. That's our goal. Okay, so how will this vector space will eventually be useful for counting holes and all that, we will discuss later. At this point, the only goal is to construct a vector space. Sorry. Yeah, so our only goal is to construct this vector space corresponding to the p faces in delta, right? So to begin with, let calligraphic f to the power p of delta be the set of p faces in delta. So this is basically the collection of all p dimensional faces in delta, and we will define this set now. Okay, so look at this very carefully. Look at this definition very carefully. So what do we do? Cp of delta. Okay, so let's first understand what are the different symbols over here. The delta over here refers to the simplicial complex that is of interest to us, and the p over here refers to the dimension that is of interest to us, right? So this automatically tells us that we construct a vector space for each p. Okay, that's what we are doing, and at this point we have fixed some p, and we are looking at some set at this point. Okay, so what does this set include? Well, the set includes elements of this form, right? So let's go over it one by one. So the elements of in this set are sums of this form, right? So let's go over it one by one. So first, notice that the summation index actually goes from 1 to little fp. So what is little fp? Well, little fp is the cardinality of this calligraphic fp of delta. Okay, so recall, what is this? This is the set of all p-dimensional faces in delta. So the cardinality will tell us the number of p-dimensional faces in delta. Okay, so fp, little fp, refers to the number of p-dimensional faces in delta. So this summation actually goes from I equals 1 to fp. Now you see these sigma i's here. Well, these sigma i's, that is sigma 1, sigma 2, sigma 3, and so on, sigma 1, sigma 2, all the way up till sigma fp, these are the different p faces in delta. Okay, so these are the different P phases in delta, right? And what are these AIs? Well, AIs are numbers taken from Z2, right? So this is what this CP of delta means. So CP of delta means you look at all such sums, okay, where AIs, okay, these AIs that you have over here, these come from Z2, and these sigma i's are basically, I mean, sigma I refers to the ith P phase in delta. Okay, and you look at these formal sums, right? So when I say formal sum, it means that, you know, when I write 2 plus 3, right, you sort of say what is 2 plus 3, your answer would be 5, right? So here you see that I am looking at formal sums, right? So these by themselves don't have any meaning, so we are just constructing them, okay, as you know, some abstract objects. That's why we call them as formal sums. So let's look at some example to get some understanding of what I mean over here. Okay, so let's say we have the following simplicial complex, okay, delta, and these are the different phases in delta. So pictorially we can denote delta in the following way. So we have three vertices v1, v2, v3, right? And we have three edges, v1, v2, v1, v3, and v2, v3. Okay, sorry, v1, v3, and v2, v3. Okay, so again a note on the notations, right? So although I write this as v1, v2, v3, v1, v2, v1, v3, and v2, v3, they actually should mean, okay, so this I should write it as calligraphic v1, because delta is a collection of sets, remember. Okay, so similarly when I write v2, it should be interpreted in this fashion, and similarly when I write v1, v2, it should be interpreted as v1 comma v2. Okay, however, as I said before, okay, this sort of unnecessarily complicates the notations. Okay, and because of these reasons, because of this reason, okay, I will simply write v1 as this. Is this okay? But you have to keep in mind that when you know, v1 is a set, okay, so here v1 actually represents this set. Okay, and when v1 is actually thought of as an element of a set, okay, so all those things must be clear to you from the context. All right, okay, so this is the simplicial complex that has been given to us, and our goal is to construct this vector space. Okay, and we will refer to each element of this vector space as a P chain. Okay, we will refer to each element of this set at this point. So I shouldn't say vector space, because we haven't shown that this is a vector space yet. So each element of this set, we will refer to it as a P chain. All right. Okay, so let's look at this example, right? So first let's understand what is the dimension of the simplicial complex. Okay, so this simplicial complex has faces of dimension 0. It also has faces of dimension 1, right? And you can see that the largest dimension is 1 over here. That's why the dimension of this simplicial complex is 1, right? So we are interested in looking at C0 of delta and C1 of delta. Okay, so this is what is our interest right now. Okay, so let's try to construct this. Okay, so what is C0 of delta? In order to construct C0 of delta, first let's look at this calligraphic F0 of delta. This is basically the collection of all zero-dimensional faces in this simplicial complex. I hope you agree these are V1, V2, and V3, right? So what is C0 of delta? Well, C0 of delta is A1 V1 plus A2 V2 plus A3 V3 such that AI belongs to Z2 for all I, right? So this is what your C0 is. So you have to look at all such formal sums. Is that okay? So let's look at all such formal sums. Okay, to begin with, what we will do is we will let A1 be 1, right? So to begin with, we will let A1 be 1, A2 be 0, and A3 be 0. So ideally, I should write it as 1 V1 plus 0 V2 plus 0 V3, right? And this, for convenience, I will write this entire thing as simply V1. Is this okay? So for simplicity, I will write this entire expression that I have over here simply as V1. Okay, so this is actually V1 over here. So similarly, okay, I can write 0 V1 plus 1 V2 plus 0 V3. Okay, so this entire thing, okay, again for convenience, I will interpret it as, okay, so again I will interpret this as simply V2. Okay, and in the same way you can interpret V3. Now let's try and understand what is V1 V2, V1 plus V2, sorry. So V1 plus V2, as you must have guessed, is 1 V1 plus 1 V2 plus 0 V3. Is this okay? So this is what it is. And I hope you agree that, for convenience, we can write this thing as V1 plus V2. Now you can similarly interpret what V1 plus V3 is, what V2 plus V3 is, and then you have this V1 plus V2 plus V3, and it is not difficult to guess that, okay, this is the formal sum 1 V1 plus 1 V2 plus 1 V3, right? This is what I will refer to as V1 plus V2 plus V3, and finally you have 0, okay, which is basically 0 V1 plus 0 V2 plus 0 V3. Is this okay? So this is what this set is all about. So you can see that this set consists of all formal sums of these different zero-dimensional faces. So you see that there is V1, there is V2, there is V3, and so on and so forth. So again, I would like to emphasize that when I'm talking of C0 delta, when I say V1, I actually mean 1 V1 plus 0 V2 plus 0 V3. This is the formal sum, right? So you shouldn't interpret this V1 as a set, right? So depending on the context, okay, I will lazily write it as V1. However, depending on the context, you should be able to interpret what this V1 means, what this V2 means, what this V3 means, and so on. Okay, so similarly, let's try and construct this C1 delta. Right, so for C1 delta, we first have to recall or first have to write down what is this calligraphic F1 delta. Well, this is the collection of all one-dimensional faces. So you can see that V1, V2, V1, V3, V2, V3. These are the different one-dimensional faces in delta. And now I have to write all possible formal sums. So you can see that I have V1, V2, so which is 1 V1, V2 plus 0 V1, V3 plus 0 V2, V3. Is this okay? So this is equivalent to V1, V2. Similarly, you have V1, V3, V2, V3, and so on. And finally, you have this V1, V2 plus V1, V3 plus V2, V3, and you also have 0. Okay, so the 0 again here refers to, the 0 here again refers to 0 V1, V2 plus 0 V1, V3, okay, plus 0 V2, V3. Is this okay? So via this example, I hope every one of you is familiar with what these different formal sums mean. In particular, if I give you a simplicial complex delta and if I give you a P, I hope you will be able to construct this CP of delta. Okay, so if you have any questions with regards to this construction of this set, this may be a good point to ask. Yes, Deep, go ahead.
When you write V1, V2 here, you mean the element-wise product of the two vectors, if I
This
see
is
them
not
as
a
well.
product. Okay, this is not a product. Okay, so as I said, so let's just recall what is this C1 delta supposed to represent. So C1 delta is supposed to represent all linear combinations, sorry, all formal sums, sorry for using that word, all formal sums of the form, okay, A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3, where AI is an element in Z2 and sigma I is an element in F1 of delta. Is this okay? So what are the different faces? So you may ask, why have I only written sigma 1, sigma 2, sigma 3? Well, the reason is that in that example that we are considering, okay, which is this example over here, this is the example that we are looking at this point. Okay, it only has 3 one-dimensional faces, right? So sigma 1 over here, we can let sigma 1 be this let's say V1, V2. Okay, this sigma 2 is basically V1, V3, and sigma 3 is, let's say, V2, V3. Okay, so the question, I mean, the answer to Deep's question is, what is this V1, V2? Well, this is not a product. Okay, this is actually a set. So let me go at it step by step. So sigma 1 here refers to a set. Okay, this set is made up of these two vertices V1, V2, right? And when I write V1, V2 over here, this actually represents the formal sum 1 V1, V2, 0 V1, V3, 0 V2, V3. So you can alternatively interpret this as 1 sigma 1 plus 0 sigma 2 plus 0 sigma 3, where the sigma 1, sigma 2 and sigma 3 are as we defined over here. Does that answer your question, Deep?
But so now I have one more doubt.
Yes.
When you say add here, so you mean union, right? Because there are sets here. You're
So
adding
that's what I
sets.
said. This addition here at this point has no meaning. We just write it in this fashion. Is that
Okay.
okay? You shouldn't
Okay.
interpret it like I am doing 2 plus 3. Is
Okay.
this okay?
Okay.
At this
Okay.
point, when I write, V1 plus V2, you shouldn't say V1 plus V2 is, I'm taking some union, because you are giving this interpretation. I have not given it. Is that okay? So
Okay.
please don't give any additional interpretation to what is being said here.
Okay.
This is a formal sum. So when I say something is formal, I'm saying it is abstract. It has no meaning. Is
Okay.
that okay?
Okay.
You just are supposed to write it this way. Why you are supposed to write it this way? We will later on see that this will enable us to count these holes. How will it enable us? Well, we will see it later. At this point, we don't want to, bring in too many things and, get confused. At this point, we are just constructing this space. Is this okay?
Yeah. Okay. Yeah.
All right. Jacob, please go ahead and ask your question.
Since this is a vector space, the scalar
I mean, it's not yet a vector space. At this point, it's just a set. So recall that for a vector space, we should also have this addition, scalar multiplication operations defined, which we will do now. At this point, it's just a set. Okay?
Okay. Okay.
Mm-hmm. All right. Are there any more questions? See, these are, I mean, if you haven't dealt with such things before, okay, and if you are dealing with these things for the first time, it may seem a bit weird. What is this addition and so on and so forth? Well, recall that why is 2 plus 3 5? It's not because 2 plus 3 is, actually 5. It's because we as human beings have defined it to be 5. Okay, that's the reason 2 plus 3 is 5. And why we have defined it to be 5? Because it serves some purpose, right? In the same way, what is this V1 plus V2? Okay, so this is a question that you could ask. Well, I'm going to tell you how it is going to serve some purpose for us eventually. At this point, it is just V1 plus V2. So I'm, asking you to think of 2 plus 3 as just 2 plus 3. I'm asking you, don't think of this as 5, because you are giving it some meaning, right? And at this point, I don't want you to give any additional meaning to V1 plus V2. It's just some sum. There is nothing like union. There is nothing like intersection, nothing like that. It is just some sum, and we will refer to this as a formal sum. Okay, so the word is, it's a formal sum or an abstract thing. Okay, so abstract means at this point it has no physical meaning. All right. Okay. So now recall what our goal was. Our goal was to construct a vector space. Okay, so so far what we have done is we have constructed this set for this P, right? So we chose a P which lies between 0 and the dimension of the given simplicial complex, right? And for this chosen P, we defined this CP delta to be this collection of formal sums, right? Where AIs come from Z2 and the sigma i's come from this set of p-dimensional faces. All right. Okay, so I gave you an example how your C0 delta will look like, how your C1 delta will look like, and so on. Right. So far, so good. Now we have to define this addition operation, and we will define a scalar multiplication operation. Right. So why are we doing that? Because I want to come up with a vector space. Is this okay? That's the purpose. Now, why are we coming with a vector space? Well, all those things will become clear later on. Is this okay? So at this point, my goal is only to come up with a vector space, and I will define an addition operation, right? So the addition operation should take as input two elements of this CP delta set, right? So that's what I have said over here. The input to the addition would be two elements from this CP delta, and the output will lie in CP delta. Is that okay? And how is the addition operation I am defining? So here is the addition, and here are two inputs from CP delta. Okay, so let's look at the two different inputs. Okay, so the first input is of the form I equals 1 to FP AI sigma I, and the second input is of the form I equals 1 FP AI prime sigma I. So what I'm saying is that this is the first element from CP delta. So I have chosen some AIs, and in the second element from CP delta, I'm choosing some different AIs. Okay, and I refer to them as AI prime. So you can, for example, in the above example, okay, I mean in that this simple simplicial complex. So let's say P is 1, or let's say P is 0. Okay, your first P chain could be like V1, and the second P chain could be like V2 plus V3, or V1 plus V3, right? So you will interpret V1 as 1 V1 plus 0 V2 plus 0 V3. Okay, so this is what is over here, and then this V1 plus V3, you will interpret it as 1 V1 plus 0 V2 plus 1 V3. Okay, so this is what we have, and this is what is present over here. Is this okay? So these are the two P chains, right? P chains are, recall, elements of the CP delta set. So I'm taking two P chains and I'm trying to add them up. right? And I am now going to define how you should add them. I am now going to define it. Okay, so how do you are supposed to add it? Well, what you do is you take these corresponding AIs, AI and AI prime, and you add them, right? So you add AI and AI prime, whatever is the resultant, you write it in front of sigma I and look at this formal sum, right? So now you can ask me, well, how do I do this addition? Well, I'm saying that look, AI and AI prime are elements of Z2, right? So AI and AI prime are both elements in Z2, right? So Z2 comes with its own addition operation. So you know how to add them. I have already told you how you can add them. So you take that addition operation and add this. Whatever is the result over here, okay, you put it in front of sigma I and write this formal sum. And in this way, you can define the addition operation. Okay, so let me pause here for a second or two. If you have any question on how we have defined this addition operation, please ask. Let me know if you have any questions on this addition operation. We have defined this addition operation. Is this okay? Okay, so just to give an example, V1 plus V3. Okay, so this you have to interpret as 1 V1 plus 0 V2 plus 0 V3, and this you have to interpret as 1 V1 plus 0 V2 plus 1 V3. Okay, and the rule, so when you want to add them up, this will be 1 plus 1, which is 0 V1 plus 0 plus 0 is 0, so 0 V2 plus 0 plus 1 is 1, so this will be V1 plus 1 V3. So we will write this for convenience as just V3. So what we are saying is that if you try to add V1, this is one of the P chains, so this is one of the 0 chains, and V1 plus V3 is another 0 chain. So you're trying to add them up, and I'm claiming that by this, if you follow this addition rule, you will end up with simply V3. Okay, that's how this addition rule is defined. Is this okay? All right. So now let us advance and define a scalar multiplication rule, right? So how does the scalar multiplication rule go? It takes as input one element from the field, and the field that we are interested in is Z2, and one element from this set, which is CP delta, and the output will be another element in CP delta. And how are we going to define? So you take some X from Z2. So this is the input from Z2. This is how I'm defining the scalar multiplication operation. And you take some element from CP delta. So you take some P chain. Okay. So you take some element from Z2 and you take a P chain. This scalar multiplication operation is defined in the following way, right? So what do? I take X and I take AI. I take their multiplication. Now recall that X and AI both lie in X comma AI, both lie in Z2, right? So since they both lie in Z2, they have a multiplication operation defined. So do that multiplication over here. Whatever is the result, right? Write it in front of this sigma I and look at this formal sum, right? So just to give you an example, right? So 1 is an element of 0, is 1 is an element of Z2. So 1 times, let's say V1 plus V3, right? So this will simply be, so 1 times 1 V1 plus 0 V2 plus 1 V3. Okay, so this will simply be 1 times 1 V1 plus 1 times 0 V2 plus 1 times 1 V3, and this will be 1 times 1 is 1, so 1 V1 plus 1 times 0 is 0, so 0 V2 and 1 V3, which I'll simply write it as V1 plus V3. Is this okay? So 1 times V1 plus V3 is simply V1 plus V3, right? So of course, to most of you, it may seem, oh, what is happening here? This is some weird operation that is happening. Of course it's weird, but if you think about it, we are being very rigorous. Okay, we are explicitly defining what this multiplication is, what is this addition is, and so on and so forth, and there is no, we are not allowing any space for ambiguity. So the vector addition and scalar multiplication operations are explicitly defined, and now we claim that this set CP delta along with this field Z2, and on top of that, if we have this addition and scalar multiplication operations that we just defined, together forms a vector space. Okay, and over the next couple of minutes, we will formally verify that this indeed is a vector space. But maybe this is a good place to stop for a few seconds and inquire if some of you have questions with regards to this addition and scalar multiplication operations. Please let me know. Any questions? All right, so I don't see any raised hand, so maybe we can advance. Okay, so our goal is to show that this CP delta is actually a vector space. So if you recall the definition of a vector space, you will see that the first thing we have to check is if this CP delta along with this addition operation that we just defined should be an abelian group. Yes, Agnit, please go ahead.
Would you comment something about the chosen field Z2?
So your question is, why are we working with the Z2 field? Well, the answer to that is it makes our life very easy. That is the first thing. But you could also ask, can we choose some other field over here? Well, the answer is that indeed you can choose some other field, but we will have to define certain things differently. Okay, and you will, I mean, maybe I'll comment later on what those different things have to be. So the answer is that indeed, yes, you can choose a different field over here. However, we choose Z2 because it serves our purpose, and it's it is going to be very easy for us to work with Z2. Okay, so it serves our purpose, that is, it helps in computing the homology in the way we desire, and second, it keeps our life very, very simple. Okay, that's the reason we choose Z2. Okay, but you could also ask, could we have chosen anything other than a field here? Okay, so the answer is that yes. I mean, this is just for someone who is interested in, not of something that we will talk about in this course. Okay, in fact, I had talked about it in the last time I had taught, but then I realized that it unnecessarily complicates things. So this time I decided not to include it. Okay, so instead of a field over here, we could also have something called as a ring. Okay, so I don't know how many of you are aware, but if you look at the set of integers, it is a ring, but it is not a field. And the reason the set of integers is a ring and not a field is that this doesn't have a multiplicative inverse, right? The elements in Z do not have a multiplicative inverse. Okay, so no multiplicative inverse. So no multiplicative inverse. Like for example, if you look at 2, okay, so you know that the multiplicative identity is 1, and there is no element in the set of integers such that a times 2 is 1, right? So we know that the number has to be half, but half doesn't lie in the set of integers. That's why Z is not a field. It's instead a ring, right? So if that was the case, so I'm saying that we can define things in that generality, that instead of working with field coefficients, we can work with ring coefficients. And in that, the claim would be that this actually forms something called as a module. Okay, so I mean, we can all study all these things if you are interested in, but this course will focus on only working with these field coefficients that come from Z2. And as I emphasize, the reason why we work with Z2 is that it serves our purpose, and secondly, it keeps lives very, very easy. Agnit, I hope that answers your question. Okay.
Yeah, thank you.
All right. Okay, so now our goal is to show that this is a vector space. And if you recall that definition of vector space, you will see that the first thing that we need to show is that if you look at this set and along with this addition operation, then we have to show that this is an abelian group. And if you recall the definition of an abelian group, we have to verify 4 properties: associativity, commutativity, the existence of an identity element, and the last is the existence of an inverse element. Okay, so we will quickly go over this. I'm going to do it a bit rigorously so that you also, when you do your assignments, exams, and in general in your life, whenever you give arguments, you make a rigorous case for it. Okay, you don't be like non science people where they just share opinions and expect you to believe that those opinions are facts. Is that okay? So in science, okay, we don't give lot of importance to your opinion or my opinion. So my opinion is as useless as your opinion. Okay, what matters is, okay, is there like a consistent way in which we can argue things out? Is that okay? So hopefully when you graduate out of IISc, okay, you will stop giving importance to opinions, but rather to concrete arguments. Okay, and that's the reason, even though it may look a bit dry, okay, I'm going to be very rigorous about this so that you can also implement this in the way you argue things out. All right, so recall what we want to do. We want to first prove associativity. So what does associativity mean? So recall if we take 2 elements from this, so let's say C is one chain, P chain from CP delta, and let's say CP prime is another P chain from CP delta, and let's say C double prime is the third P chain. So what we want is that the way in which you add these things doesn't matter. Okay, so let me just write this first down and then I'll explain. Okay, so on the left, what I'm saying is that you first add C and C prime, whatever is the result, you take that and to that you add C double prime. Okay, so this is one way in which you can add three terms, right? On the right hand side, what you do is you first add C prime and C double prime. You first add them, whatever is the result, you take that result and you add to C. And now what we are wanting to check is that if the order in which we add things matters or not. And what we are going to claim is that that doesn't matter. Okay, so let's see why. So here is one P chain, here is another P chain, and here is the third P chain, right? So notice that the differences between these three P chains is that here you have AI, here you have AI prime, and here you have AI double prime. So in that way, we have three different P chains. Okay, and by the way I have placed these round brackets, it indicates that I'm going to first add these two P chains. Whatever is the result, I will take that and add it to this P chain. Okay, so that is what I'm going to do over here. So from the addition operation that we defined previously, I hope you agree that this, once we add, will be AI plus AI prime. Okay, and we will write that as a coefficient of sigma I, and we will end up with this formal sum. So whatever is this formal sum, now I'm going to take it and add it to this formal sum, right? So this formal sum plus this formal sum would be this, that is AI plus AI prime. So notice the way I have put this round bracket plus AI double prime. So this round bracket over here emphasizes that I have first added AI and AI prime. Whatever is the result, I'm going to use that and add it to AI double prime, right? So this is what I would end up with if I do the addition in this order. That is, I take this P chain, add them up, right? And then whatever is the result, I add it to this P chain. Is that okay? So if I follow this order, I hope you agree that this is the formal sum that I will end up with. But then I notice that the addition that is being performed in this big round bracket, the addition that I am performing in within this big round bracket is addition of elements from Z2. Now Z2 is a field, which means that the addition operation and Z2, that is the set, together they form an abelian group. So there the associativity property holds. So the order in which I add this AI, AI prime and AI double prime doesn't matter. So I can write this in this sense. Okay, this is because the reason for this way of writing is that since Z2 comma plus is an abelian group, which implies that the addition there is associative in nature, right? So because of that reason, you can see that we can write it in this fashion. However, this and this are one and the same. This is because of the way we define the addition operation, and finally we can write this in the following way. So you can see that what we have ended up with, okay, in this we add these two P chains first. Whatever is the result, we take that result and add it to this P chain over here, right? Whereas when we started off with, notice that the order in which we added the P chains was different. Okay, so by verifying that this way of adding and this way of adding is one and the same, we can now conclude that the order in which we add doesn't matter, right? So in fact, I can write this formal sum without worrying about where the brackets are, because it doesn't matter how you add them. Okay, so I can in fact write it in this fashion without putting any brackets. Is this okay? I don't have to put these brackets because howsoever you decide to add these things, you would end up with the same answer. So let me pause here. If you have any questions with regards to the way we verified associativity, please ask. Let me know if you have any questions. Okay, this is the level at which I expect you to write your assignments. This is the level at which I expect you to write your midterm exams, final exams, everything. So there is no final exam, but this is how we will interpret it. All right. So I don't see any raised hands. So let's advance. Okay, so I mean, I sort of helped you prove this associativity property. I hope in the same way, each one of you would be able to verify this commutativity property as well. So I will leave that as something that You can try it on your own. Okay, so now the next thing that we will verify is the existence of this identity element, right? So what we want is that, so let's recall what one identity element means. So we require an element E in G such that A plus E equals A equals E plus A. Okay, so this is the thing that we have to check. So first let's see what is a candidate identity element. Well, the candidate identity element is 0. So although I have written it as 0, you have to interpret it as 0 sigma 1 plus dot 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 0 sigma fp, where recall this little fp denotes the number of p-dimensional faces. Okay, all right. So what I'm going to do is I'm going to verify this part, that is A plus E is A equals E plus A, right? So I'm going to take some arbitrary p chain. To that I'm going to add this identity or potential identity element that we have identified. So recall what this 0 is. Well, this 0 is just summation I equals 1 to fp 0 sigma I, right? So this is what I'm supposed to add. So if I try to add this here from the rules of our addition, what we have to do is we have to add the corresponding coefficients, which is ai plus 0, and write that as the coefficient of sigma I, right? So this is ai plus 0, right? However, we know that this 0 is the identity element in the field, right? This 0 over here is an element of Z2. This is the identity element of the field Z2. So ai plus 0 is ai, and ai plus 0 is ai, and this is also 0 plus ai, right? So I hope you agree that this three relations or these two relations follow from the fact that Z2 plus is an abelian group, right, where 0 is the identity element, right? So this 0 over here refers to an element in Z2, right? So this refers to an element in Z2, whereas when I write 0 over here, okay, this refers to an element in CP delta, and this is what its interpretation is, right? So depending on where I write 0, you have to carefully interpret what that 0 represents. Okay, so just don't blindly imagine that this 0 is an element of Z2, whereas this 0 is an element of CP delta, and so on and so forth, right? So notice that this addition is defined only between elements of CP delta. So you cannot have an element in CP delta and an element of Z2 and you can try to add them. So it can never happen, right? So depending on the context, it should be clear to you what I'm trying to add. Okay, so I hope you agree that these two relations hold, and from this this I can write it as 0 sigma I, the sum of them, and this is summation ai sigma I, and this is basically 0 plus 0 ai sigma I, right? So we have verified that indeed this plus 0 is this equal to 0 plus summation ai sigma I, right? So we have verified this property that we stated over here, and because of this reason we have managed to show that indeed there exists an identity element, right, which satisfies the desired properties. Okay, so the final thing that we have to verify is that there is an element, there is an inverse element for every element in this set, right? So the claim is that every element is its own inverse, right? So let's just verify. You take this element and add it to itself, right? Now from the rules of addition, I hope you agree that we would end up with summation I equals 1 to fp ai plus ai sigma I, right? Now whatever be this ai, I don't know what these ais are, but whatever be these ais, right, like either ai could be 0, in which case ai plus ai will be 0 plus 0. I hope you agree with me that we will end up with 0, or alternatively these ais could be ones themselves, in which case I'm taking 1 and adding it to 1, and I hope you recall from the addition operation on Z2 that 1 plus 1 is also 0, right? So because of this reason, ai plus ai, whatever be ai, this will always be 0, right? So I hope you agree that this will result in summation 0 sigma I, which we have identifying as the identity element, right? So this equals 0. So you can see that you took an arbitrary p chain, and we are claiming that it has an inverse, and it is a special inverse because the same element is its own inverse. So you take this element, add it to itself, and we get back the identity element. So with this, we have managed to show that CP delta along with this addition operation is an abelian group as desired. Okay, so let me pause here for a couple of seconds. If you have any questions, on how we went about verifying that this is an abelian group, please ask. Otherwise, we can advance with verifying the properties of the scalar multiplication. Let me know if you have any questions. You can ask me as simple a question as you like. Please don't hesitate. Whatever questions you have, please go ahead and ask. Okay, everybody is learning it for the first time, hopefully, or perhaps some of you have some background, but nevertheless, don't hesitate. Don't think that you are the only one who is not understanding. Please ask questions. Please feel free. Okay. All right. So I don't see any raised hand, so maybe we can advance. Okay. So now the next thing that we have to do, so recall our original goal. Our original goal is to show that this CP delta is a vector space. So we managed to prove part of it, that is the CP delta and the addition operation is an abelian group. We now have to verify the properties of the scalar multiplication operation that we have defined, right? So recall the three properties. One is this identity property. The other is this compatibility property, right? And the third is this distributivity property. Okay, so identity element means that 1 dot v is v for every v in your set, right? Compatibility means that so let's say x dot y dot v equals x dot y dot v, right? And the distributive property, we have to verify two things. One is that x dot u plus v equals x dot u plus x dot v, and x plus y dot v equals x dot v plus y dot v. Okay, so here your x and y's are elements of your field, and u, v, etc. Those are all elements of your set. Is this okay? So these are the three properties that we will now try and verify with regards to the scalar multiplication property that we have defined. Okay, so let's look at the first thing, which is the identity property, right? So what we have to do is we have to take the multiplicative identity in the field. So the multiplicative identity in the field is 1. So we take that and take some arbitrary p chain, okay, and we do the scalar multiplication operation between them, right? So from the scalar multiplication operation that we have defined, what we have to do is we have to multiply this element to every ai that is present inside, right? So this is the formal sum that we end up with. But 1 dot ai, whatever be ai, I hope you agree is simply ai, and we end up with this p chain. So you can see that the p chain that we started out with, we end up with that same p chain, and in other words 1 dot this is equal to this, and in that way I hope you agree that we have verified this identity property. So let me pause here for a second or two. Let me know if there are any questions with regards to this identity property verification. Okay, do you have any questions? All right. Okay, so maybe we can advance. So the next is this compatibility property. Okay, so here what we are saying is that let us say we have been given two elements in Z2. Okay, so let us say we have been given two elements in Z2, right? And let's say we perform the scalar multiplication operation in this fashion. So let us try and understand what is happening. So you take some arbitrary p chain, right? So you take some arbitrary p chain, okay, and first do the scalar multiplication with this element in Z2. Whatever is the resultant p chain, you take that and you perform the scalar multiplication operation with this element from Z2, right? That's what we are trying to do. So this way we are putting in the brackets will make it clear what we are doing. So this is the p chain. You take that and multiply it with y, which is the first scalar multiplication that we are doing. Whatever is the resultant p chain, you take that and to that you multiply x. Okay, so let's try and do this. So y dot this, I hope you agree, is summation I equals 1 to fp y dot ai sigma I. This is from the definition of the scalar multiplication operation. And now whatever is this p chain, I'm going to multiply it with x. So this will end up with x dot y dot ai round bracket sigma I. So let us just understand what this is. So I emphasize that this multiplication over here is the scalar multiplication. Okay. So although I'm using the same notation, again from the context it must be clear what I'm talking about. This is the multiplication in the field, right? So this is the multiplication in the field. So how do you distinguish whether I'm talking about the scalar multiplication or multiplication in the field? You have to look at the inputs that I'm giving to the multiplication operation. So here you can see that the input is element of Z2, and the second part of the product is an element of your CP delta. Whereas here you can see that the two inputs are elements of your field itself. So from this it should be clear whether I'm talking about multiplication in the field or whether I'm talking about multiplication in the the scalar multiplication operation. Okay, so I think I should have been a bit more careful here. I should write it in this fashion, and because the multiplication property in a field is associative. Okay, I can ignore the order and write it in this fashion. Is that okay? Write it in this fashion. Okay, so this is how I can write this entire product as. Okay, and sorry, there is a mistake here. This should actually be AI sigma I, right? So I hope you agree that summation x dot y dot AI sigma I, right? This entire thing from 1 to FP, okay, is equal to this, right? So I take this x dot y outside and I multiply it in this fashion. So you can see what I have written over here, right? What I have written over here, sorry, what I have written over here equals what I have written over here, right? So of course, algebraically I've written something. Let's first try and interpret what this means. It means that the order in which you perform the multiplication, okay, it doesn't matter. So what the left hand side says is that you take a p chain, do the first scalar multiplication, whatever is the resultant p chain, you perform the final scalar multiplication. Whereas what we have over here is you take these two scalars, first perform the scalar multiplication in the field, or I should say the multiplication in the field. Whatever is the output, you use that to perform this scalar multiplication, and it doesn't matter the order in which you perform, you will end up with the same output. Okay, and in the same way, I hope each one of you would be able to verify the distributive property as well. Okay, so the distributive property requires us to show something like this. Okay, so I encourage you to go over it and verify that indeed, okay, the distributive property actually holds. Is this okay? So in this way you can verify everything, and you can indeed conclude that CP delta is a Z2 vector space. Okay, so let me pause here for a couple of seconds if there are any questions with regards to how we went about defining the addition operation, how we went about defining the scalar multiplication operation, and how we verified that this addition and scalar multiplication, the way we have defined, ensures that this CP delta is actually a Z2 vector space, right? So if you have any questions on this, please let me know. There are some parts which I didn't go over, but you can go back home and sit and verify it on your own. I have sort of given you the broad idea how you should be able to verify it, and from that I hope you agree that we have managed to show that CP delta is indeed a Z2 vector space. Okay, so let me pause here for a second or two. If you have any questions, please ask. Okay, so again, one of the questions that there may be in your that may be there in your mind is that, oh, why are we doing all this? Okay, so as I said before, please be a bit patient. Okay, I don't want to talk about several things at the same time, why it is useful and so on and so forth. So hopefully by the end of today's class itself, it will be clear what we are trying to do and why we are trying to do it. Yes, Ichit, please go ahead.
Sir, actually I want to ask that formal sum, that is sigma, you have used here, and the plus sign, plus operator we have used here, are both they are same or different?
This plus sum you mean?
Yeah, and sigma means you for the
so let me just understand. So what you are saying is that, okay, let me just understand. So what you are saying is that in the formal sum, we had A1 sigma 1 plus A2 sigma 2. I mean, let me just write it properly. So what you are saying is that we have this,
yes,
right?
yes.
So let me write it. This is there, AI sigma I. And now you are saying that, so now you are asking, oh, we are also talking about something like this, right?
Yes.
So your question is this addition that we have and this addition that we have, A1 sigma 1 plus blah 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 plus AFP sigma P, is this addition and this addition the same? Is that your question?
Yes, sir. Yes.
Okay, so good question. Okay, so let me try and answer this. See, when we defined the set, right? So if you recall, we defined this CP of delta, right? So there itself we said it consists of elements of this form, right? So like it is A1 sigma 1 plus blah 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 plus AFP sigma FP, right? So this is what I said. Okay, so now you could have asked, what does this sum over here mean? Well, at that point I would have said, well, these sums don't mean anything, right? Now we have in addition defined an addition operation. Okay, so now we have a separate addition operation that is defined, and you can ask, what do these additions now mean? Well, I can say, well, you can interpret this addition that you have and this addition in the same way, and you can do it in the following way. I hope you agree that when I write A1 sigma 1, right, this itself is a P chain. What is this P chain? Well, this is A1 sigma 1 plus 0 sigma 2 plus blah 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 plus 0 sigma FP. Do you agree, Ichit?
Yes. Yes.
And similarly, I can interpret this A2 sigma 2 as A1, as 0 sigma 1 plus A2 sigma 2 plus blah 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 plus 0 sigma FP. Now, if you take these two P chains, that is this, and if you try to add them by the rule that we have specified, I hope you agree that we would end up with A1 sigma 1 plus A2 sigma 2 plus 0 sigma 3 plus blah 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 plus 0 sigma FP. Is this okay? And you can, for convenience, you can write this as A1 sigma 1 plus A2 sigma 2. And I hope you agree that by generalizing this idea, you can interpret A1 sigma 1 plus blah 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 FP sigma FP as A1 sigma 1 plus A2 sigma 2 plus blah 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 FP sigma FP, right? So you can ask, oh, what have I done here? I'm just adding things and I'm adding the same thing. Well, the way I want you to interpret is that this I want you to interpret as A1 sigma 1 plus 0 sigma 2 plus blah 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 plus 0 sigma FP. Similarly, I want you to interpret this as 0 sigma 1 plus A2 sigma 2 plus blah 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 0 sigma FP and so on. Is this okay? So indeed, when I write this formal sum, you can interpret these individual things as these special P chains, and you can interpret this entire addition as if you are adding these individual P chains. Does that answer your question, Ichit?
Yes, sir. Sir, but one more question I have.
Mhm.
Sir, while defining the plus operator, we have used brackets and associativity for separating out the scalars.
Yes.
Okay. So in that case, automatically the distributivity property is coming into picture, I guess.
So let's just think about it. Okay, so let's just go to the addition operation, right? So here is the way we define the addition operation. Is this okay?
Yes.
So we take one P chain, we take another P
Yes.
chain, and we are saying this is
Yes.
how we add them. Now your question is, does
Yes.
this automatically imply the distributive property? Well, the answer is not really, because this is one P chain, right? So let's
Yes.
verify the distributive property. So what I'm supposed to do is, you take some element is x in Z2, right? Do the scalar multiplication, right? And I want to show that this equals x dot summation ai sigma I plus x dot summation ai prime sigma I. Do you agree? This is what one of the distributive properties is.
Yes, sir.
So you can see that in the addition property, there is no scalar multiplication, right? So that by itself doesn't say anything about distributive property, because the distributive property concerns how scalar multiplication and the addition behave in combination with each other.
But sir, AI sigma isn't it means
I mean,
scalar
of course, by
multiplication?
using this, we can verify this property. If you are saying that using this, we can verify, of course, that's what we do. but I'm saying that the addition property itself doesn't say anything about distributivity, because the addition property doesn't have any scalar multiplication being used to define the addition property. Is that okay? Or the definition of addition?
Okay.
Is that okay?
Okay, sir.
I mean, see, you have to be careful. You have to be able to distinguish between intuition and rigorous verification. Is that okay? So the rigorous verification is what we are trying to do over here, that this property is true, right? Intuitively, one can see that indeed these properties must be true, because at the end of the day we are only manipulating things in Z2. Is that okay? Right?
Yes.
All right. Okay.
Okay, thank you.
Sure. So are there any more questions? Please ask. All right. I'll wait for a second or two. If there are any questions, please ask. All right, so I don't see any raised hand, so maybe we can advance. Okay, so now what we have done so far is we have managed to show that this CP delta is indeed a vector space, right? So it's a Z2 vector space, Z2 vector space, right? So this is a Z2 vector space. So one can ask, okay, this is a vector space. What is its dimension, right? That is an immediate question that one can ask. What is its dimension? And one can ask, can we come up with a basis for this vector space? Okay, so that is what we are going to do now. Okay, so the question is, what is the dimension of this vector space? And in order to do that, or in order to answer this question, we will try and find a basis for CP delta, right? So what we claim is that a basis for this CP delta is this collection of P chains, right? So again, you have to be careful, okay, in trying to understand what I have written over here, right? So let's try and understand what is written over here. So when I write the set which contains sigma 1, sigma fp, I don't mean these sets themselves. What I mean over here are P chains. So when I write sigma 1, I mean 1 sigma 1 plus 0 sigma 2 plus blah 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 plus 0 sigma fp. Similarly, when I write sigma 2, I mean 0 sigma 1 plus 1 sigma 2 plus blah 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 plus 0 sigma fp. So notice that the elements of CP delta are P chains, right? So when I say I'm talking about a basis for this CP delta, I have to give you a collection of P chains. So what are those collection of P chains? Well, they are sigma 1 to sigma fp, which are shorthand notations to actually mean 1 sigma 1 plus 0 sigma 2 plus blah 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 0 sigma fp, 0 sigma 1, 1 sigma 2 plus 1 sigma 2 plus blah 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 0 sigma fp, and so on. Sorry about this. Is this clear? And my claim is that, okay, this collection of P chains indeed forms a what should I say? I mean, this collection actually spans CP delta. So let's verify how it spans CP delta. So why does it span CP delta? So in order to show that it spans CP delta, what do I have to show is that I have to show that you give me any arbitrary P chain. Okay, so here is an arbitrary P chain. Okay, I am claiming that you should be able to express this as a linear combination of these different P chains that I have over here. But this is obvious because I can write this as A1 scalar product sigma 1, okay, plus A2 sigma product, sorry, I shouldn't say sigma product, scalar product sigma 2 plus blah 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 plus AFP scalar product sigma FP. Right, so again you can ask, oh, what is happening here? I don't know how to multiply A1 with sigma 1. Well, you have to interpret this sigma 1 as 1 sigma 1 plus blah 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 plus 0 sigma FP. You have to interpret this sigma 2 as 0 sigma 1 plus 1 sigma 2 plus blah 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 plus 0 sigma FP, and all the way up till AFP scalar product 0 sigma 1 plus blah 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 plus 0 1 sigma fp, right? So now you can do the scalar multiplication operations the way we have defined. So this will be A1 sigma 1 plus A2 sigma 2 plus blah 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 all the way up till AFP sigma fp. Is this okay? And this is what we started off with. So you can see that any arbitrary P chain can be expressed as a linear combination of these P chains. Okay, so in this way we have managed to show that these many p chains, okay, actually span CP delta, right? However, from this we cannot conclude that this is a basis, because we also have to verify that this is actually a what should I say? This is actually linearly independent, right? So let's just verify that this is linearly independent. So in order to verify that, what we have to do is we have to take linear combinations of these different p chains. Okay, we have to take linear combinations of these different p chains. So what do I mean by that? So I'm going to take a1 dot sigma 1 plus a2 dot sigma 2 plus blah 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 plus afp dot sigma fp. So this is an arbitrary linear combination of these p chains, right? So this sigma 1, recall, is 1 sigma 1 plus blah 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 plus 0 sigma fp, right, and so on. So you can see that this is a p chain, this is a p chain, this is a p chain, and I'm taking a linear combination of these p chains and I'm setting it to be 0. Is this okay? I'm setting it to be 0, right? And so what is this 0, right? So what is this 0? So this 0 is 0 sigma 1 plus blah 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 all the way up till 0 sigma fp, right? And what we are claiming here is that, let's say there was some linear combination such that this equaled this, right? So let's say this equaled this, right? However, in formal sums, okay, two formal sums are the same only if the coefficients are the same, right? So here you have this a1 and 0, right? So this a1 and I mean, notice the coefficient of sigma 1. So in these formal sums, these two things would be the same only if a1 is 0, a2 is 0, and so on. Okay, so this sort of follows trivially from the fact that we are working with these formal sums, right? And interpreting that two p chains are different if the coefficients are different, right? So this p chain and this p chain must be the same only if the coefficients are the same, right? So this trivially follows from the fact that we are identifying or distinguishing between two p chains only if their coefficients are different, right? So from that basic fact, one can conclude that this must be 0 only if these ai's are 0 for all I, and from this one can conclude that these many fp p chains, right, these are indeed linearly independent. So from this it follows that this collection forms a basis for CP delta, and from that we can conclude that the dimension of CP delta must be the number of elements here, which is FP, which, recall, is the number of p dimensional faces, right? So what we have managed to conclude is that this is a vector space and its dimension equals the number of p dimensional faces. Okay, so let me pause here for a second or two. If you have any questions on how we went about verifying the dimension of this space, this may be a good place to ask. You have a question? All right, so I don't see any raised hand, so maybe we can advance, right? So each one of you, I hope, is slightly feeling uneasy because this CP delta consists of these weird formal sums. You are doing this addition which is also defined in some arbitrary fashion and so on and so forth. Okay, so here is a claim, okay, that will sort of help you relax a bit. Okay, so what is this claim trying to tell us? This claim is trying to tell us that this CP delta as a vector space is isomorphic to Z2 raised to FP, right? So this is some vector space which I'll tell you what it is, right? So this is a vector space, this is a vector space, and we are claiming that these two vector spaces are isomorphic to each other. So let's first understand what this vector space is, right? So in order to help you understand what this is, let's first try to understand, okay, something that is maybe more familiar to you. So let's look at the set of real numbers, right? So I hope you agree that this is a field, right? So if I ask you what is R2, what is R3, and so on, right? So of course, you can give like R2 is the collection of all these pairs of vectors or pairs of real numbers. R3 is, is made up of these triple of real numbers, and so on and so forth, right? So that is a very loose way of defining what R2, R3 and so on are. But a more formal way would be to show that R2 is actually R direct sum R, right? So this is actually, one can think of R as a vector space over itself, right? So let me write as R is a R vector space, right? So R is also a field, but R is also a R vector space, right? So what do I mean by that is, this is what I mean, right? So you can define the set to be the set of real numbers. You can take R to be the field, and you can define the usual addition and the usual multiplication operation, okay? And you can think of this as an R vector space. So this is a vector space, this is a vector space, right? And you can define, as we did in the previous class, we can take their direct sums, right? The direct sums of these vector spaces. So once we take the direct sums of these vector spaces, whatever is the resultant vector space, that is what we identify as R2. Similarly, we can look at R3 as R direct sum R direct sum R. You can also equivalently look at this as R2 direct sum R. Okay, so or R direct sum R2. Okay, so all of these interpretations are fine. If you think about it a little bit, you should be able to verify that either I can write it this way, or if it makes it, if you want to be a bit more careful, you can see that you can define R3 in your usual way. Okay, and you can say that however we define these three things, these the usual R3 and the way we construct these direct sums, these are all isomorphic. Okay, so now let's come back to what this Z2 to the power Fp is. Well, Z2 to the power Fp is, you take Z2, this is a vector space. Okay, so as I said, a field can be viewed as a vector space over itself, right? So this is a vector space over Z2, this is a vector space over Z2. You take their direct sums, and how many direct sums you have to take? You have to take Fp many direct sums. Is that okay? So let me just give you an example. Okay, so let's say Fp is 1. So let's say let's say Fp is 2. So what is Z2 to the power 2? Well, this is the collection of all elements, let's say A1, A2, such that AI lies in Z2. Okay, this is what Z2 to the power 2 is. So this means that I have elements of the form 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so this is what it means. So this is, recall the way I define these direct sums, right? I have these ordered lists where the first element comes from Z2, the second element also comes from Z2, and similarly you can define Z2 to the power 3. So this will be 0, 0, 0 all the way up till 1, 1, 1, and so on, right? So in that way you can define this Z2 to the power Fp. Yes, Jacob, please go ahead.
Sir, in the next page.
Yeah.
So in the interpretation of R3 as R2 direct sum R, so wouldn't it be an ordered pair in which the first element is an ordered pair and the second is from R?
Precisely, that is correct. Okay, so that's why I wrote this isomorphic sign over here, right? So what you are saying is indeed true, right? So when we write R2 direct sum R, okay, so this will be like X comma Y comma Z. Is this okay? Right? Whereas when we write R3, it will be like X, Y, Z. This is your worry. Is that correct?
Yeah, isomorphic. Okay, then it's.
So they are isomorphic, meaning that although the way we are writing it may be different, and you cannot say that this element and this element are the same, but you can map it in this fashion, right? So you can construct a map which takes this element to this element. Is that okay? And you can show that this is a bijection, and you will be able to show that this is also a vector space homomorphism. That is, if you take two elements of this form, so let's say x1, y1, z1, and let's say this is x1, y1, z1, and you write this as x2, y2, z2, and let's say you do this as x2, y2, z2. So indeed, the way we write it is different. Is this okay? However, they are isomorphic because if you do this addition operation and follow the addition from before, okay, and follow the addition, meaning you have to, you have to add, these two parts. Okay, so this you have to add to this, and this you have to add to this, right? And when you add this, you have to add the corresponding elements and so on and so forth. So if you follow the rules, as prescribed, you will see that this map over here is actually a vector space homomorphism, and this map is also a bijection. That's why these two vector spaces will be isomorphic to each other. Does that answer your question, Jacob?
Yes, yes.
If there is any confusion, we can discuss this during the discussion session right after the class. Is this okay? So anyways, coming back to this claim, right? So this CP delta sort of made us feel very uncomfortable because there were these formal sums and so on. So I claim that this claim over here will put us at a little bit of ease in the sense that I'm saying that this vector space is actually isomorphic to this vector space over here, that is Z2 to the power Fp, right? So so as I said, this is what Z2 to the power 2 is. It is made up of these 4 elements, right? And you can accordingly define the addition operation where you add these corresponding entries, and you can accordingly define the scalar multiplication operation and so on and so forth, and think of this as a vector space. Similarly, you can have this Z23 as a vector space where you define this coordinate wise additions and scalar multiplications and so on and so forth. Okay, and you would be able to check that this is a Z2 vector space, right? So this is a Z2 vector space. So by that I mean that this is a vector space where the field is Z2. Similarly, this is a vector space where the field is Z2, right? So all these are Z2 vector spaces, right? So in that sense, this also is a Z2 vector space, and my claim is that these two vector spaces are isomorphic to each other. And you can ask, okay, you are telling us that it's an isomorphism, so give us the map, right? So here is the map, right? So the map is it goes from CP delta, which is the vector space over here, or the set on the left hand side, to the set on the right. Okay, so what is the map? Well, you take this formal sum, which is I equals 1 to Fp Ai sigma I, and you map this to the vector where the first coordinate is A1, the second coordinate is A2, and all the way up till the last coordinate being AFP. So notice that the number of coordinates here is Fp in number, right? Because the sum goes from I equals 1 to Fp. So I hope you agree that this is an element of Z2Fp, right? So this is the map, and you will be able to check that if you take a linear combination on the left hand side, right, you will be able to verify that this this map, the way we have defined it, actually is satisfying the property that this is actually equal to x dot phi of summation ai sigma I plus y dot sum of summation ai prime sigma I, right? So ai prime sigma I, right? So this is how we can perform this. I mean, we can verify this, which shows that this map phi over here is actually a linear map, that it is satisfying the linearity property. Okay, so if you give a linear combination of inputs as an input to this function phi, okay, you can see that the corresponding output is actually a linear combination of the corresponding outputs, right? So in that way you can verify this. Okay, so it is very easy to actually verify this. So you'll be able to verify this, and in order and in that sense manage to show that this actually is a vector space homomorphism, right? And similarly you will be able to verify that this function is actually a bijection. So by bijection I mean that you should be able to verify that this function phi is actually an injective map, right? And similarly you should be able to verify that it's a surjective map. Okay, and for simplicity let's just discuss this surjective property, and you can similarly verify the injective property. So surjective property means the following. Let's say we have this phi function which goes from CP delta to Z2FP. So surjective means that every element in Z2FP should have one element, or at least one element in CP delta which gets which maps to this element. So let's pick an arbitrary element in Z2FP, which is A1, A2, blah blah blah, all the way up till AFP, where each AI is an element in Z2. Right, so this is an arbitrary element in Z2FP, and now you have to give me an element in CP delta such that under phi that element gets mapped to this. Well, it is trivially true because I just picked this linear combination AI sigma I. This is a P chain, and if I apply phi to this, this will get the output of this will be this vector, because this is how we have trivially defined this phi function, right? So in this sense you can check that this phi is a bijection, and it also satisfies the linearity property, and because of this reason, okay, these two vector spaces, okay, are isomorphic to each other. Okay, so again I say that I have not gone over the verification very carefully. This is because I spent enough time in the initial part of this class going over things step by step. Okay, and here I'm sort of glancing over things, but sort of mentioning the main milestones that we cross in order to prove the final result. But you should be able to verify it on your own, and if you have any questions, I'll be available in the next class, and you are more than welcome to ask me then. Is this okay? So now with this, what we have managed to show is that CP delta is a vector space. It has dimension little fp, and it is also isomorphic to this vector space Z2 fp. So this is Z2 direct sum Z2 direct sum blah 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 direct sum Z2. Is this okay? So this is something that we have done so far. Right now, all this discussion, that is the discussion that we have done so far, okay, concerned the choice of P that was between 0 and dimension of delta. So recall delta is the simplicial complex that is under consideration. So it has some dimension, and whatever we discussed so far concerned when P was a number between 0 and dimension of delta. Right. So one can ask, can we define these the vector space concerning P chains for P less than 0 and P greater than dimension of delta, right? So this is a bit interesting, because notice that there will be no phase. So recall how we define the CP of delta, right? So this is summation I equals 1 to FP, right? So it's the collection of all these formal sums, right? Such that AI belongs to Z2 and these sigma i's belong to calligraphic FP of delta. So this is how we define. However, when P is satisfying either this condition, right, satisfying either this condition or this condition, I hope you agree that this FP of delta will be empty, right? So this will be empty. So it's not clear how would we go about defining this CP of delta. Well, the answer to that is that as we saw, the CP deltas are vector spaces. So what we will do is we will separately or without using this definition in the literal sense, we will just set this CP of delta to be this trivial vector space which only includes some identity element which we sort of refer to as 0. So if you ask me what is this 0 over here, well, the answer is that it has no meaning. It is some identity element and we will call it as 0, right? So this is the trivial vector space. So why is this the trivial vector space? And again you can ask, what is the field over here? Well, the field again is Z2. Right, so the field again is Z2. So let's just check, if all the properties are true. Well, it has only one element, so we have to check if 0 plus 0 is, satisfying the desired property. So I hope you agree that 0 plus 0 is 0, because we are interpreting the 0 as an identity element, right? So this is the only addition that we have to, take into account. Okay, and you can see that 0 plus 0, because the fact that 0 is an identity element, it doesn't matter in which way you add. Okay, and you can see that it's also its inverse and so on and so forth, and the associativity property also trivially holds, right? So it doesn't matter how you add them up and so on and so forth. So my point is that what we have over here is a trivial vector space. So all these properties trivially hold, right? And you can similarly verify the scalar multiplication operation. So 0 dot 0, okay, so this will be 0, and 1 dot 0, this will be 0, right? So notice that I don't talk about 1 dot 1. The reason is that the first element has to come from Z2 and the second element has to come from the vector space, right, or the set, right? So the set doesn't contain 1, that is why I don't talk of 1 dot 1. I only have to talk about 0 dot 0 and 1 dot 0, and you will be able to verify that the scalar multiplication also satisfies the desired property. So in that sense, this is the trivial Z2 vector space. Okay, so whenever we define vector spaces in this sense, so notice that we now have a CP delta for all P in the set of integers. Okay, this is what we have ended up with. We have a CP delta for all P in Z, and whenever we set CP delta to be the trivial vector space for all P, we will refer to this setup as the usual homology setup, right? On the other hand, there will be certain situations which we will discuss wherein we will set Cp delta to be the trivial vector space for all p except -1, in which case we will set C -1 of delta to be Z2 itself. And I hope you agree that this Z2 is a field, but it can also be interpreted as a vector space. So Z2 is a vector space over Z2. Okay, so this Z2 is the field. Okay, so this is the field. So this can be interpreted as the vector space over itself. And my claim is that there will be certain situations, and for certain reason we will set this C -1 of delta to be Z2, in which case I will say that we are working with reduced homology. Right, so why is this reduced homology useful? Why is the usual homology useful? All this will become clear hopefully in the next class. Is this okay? So now we are sort of done with setting up. Okay, so these vector spaces are now set up. What do we do with these vector spaces will be the discussion for the next class. But nevertheless, let me give like a quick a couple of line motivation for what we'll be doing in the next class. Right, so as I introduced at the beginning of this class, here are 3 examples of simplicial complexes. Here there is no two hole. When I say no, so I should actually write one hole. Okay, so I mean these are some notations. Okay, so when I write one hole, I mean this is a two-dimensional hole. Okay, I mean this is some arbitrary way of saying why this is not referred to as a two hole but a one hole. So all these things will become clear. But whenever I say one hole, I mean a two-dimensional hole. All right. So why is there no one hole here or no two-dimensional hole here? The reason is that what have I written here? This is supposed to be a two-dimensional thing. All right. So the reason why there is no hole here is because there is no enclosed region, right? So you can see that in this example, there is some enclosed region, whereas in this simplicial complex, there is no two-dimensional hollow enclosed region. That is why there is no one hole here. Here there is a hole. Okay, so here there is an enclosed region which is also hollow, whereas in this example there is an enclosed region but it is filled. Right, so the reason why there is no hole here and the reason why there is no hole here are different. Here there is no hole because there is no enclosed region, whereas here there is no hole not because there is no enclosed region. Indeed there is an enclosed region, however that region is filled. Right, so in the next class we will be defining certain operators which will ensure that we are able to distinguish between this case, and we are able to jointly ensure that we don't count a hole in this scenario and don't count a hole in this scenario as well, whereas the operator will count a hole in this scenario. So how we define these operators and so on and so forth will be the focus of the next class. Okay, so maybe we can stop over here. Let me stop the recording.